Let's just take a look at the graph of f, and we know it is given in this figure 9.31, and we have to prove that this function is convex in minus infinity to infinity. Again, the way we proceed here is that, let us say we have two numbers a and b. These are two arbitrary numbers, and again let's take up lambda belonging to 0 to 1. We have to basically show that this is the case. If I just take a look at what is the case in this. So if I talk about the function being convex, that means we basically have to show this 1 minus lambda a plus lambda b. This is less than equal to 1 minus lambda f of a plus lambda f of b. Or in other words, if I take their difference, so it will be f of 1 minus lambda a plus lambda b minus 1 minus lambda f of a plus lambda f of b. This should be less than equal to 0. Now, we basically have to prove that this difference is always less than equal to 0. Once we have proved that, that just means the function is convex. Now, our case is f of x is equal to mod x. So, let's take up this, and this is in fact equal to mod 1 minus lambda a plus lambda b minus 1 minus lambda mod a plus lambda mod b. In fact, I should write this. I think I've made a mistake. So it should be this. And the same thing applies here. This. I know here in general, as an aside, let me write this, that if I have, we have done this earlier also, that if we have absolute value xy that is exactly equal to this. Also, if you have x plus y that is less than equal to this plus this, and this is for all x and y, for all real numbers x and y, and that means now I can go for this being less than equal to 1 minus lambda this plus lambda this minus 1 minus lambda this minus lambda mod b. And if we just pay close attention to this expression, this is 0. And that just means we have proved this. This is proved now. And therefore I can write, so this was just an aside, therefore I can write, thus f of x is equal to mod x. This is convex. And I can also see that from the diagram. Here we see in figure 9.31 the function is convex, but if you take a very close look here, it is actually not differentiable at x is equal to 0. So here we have been able to establish the convexity even for a function that is not differentiable with the help of this general definition. Now, but in general, but usually what we see is that if you have a twice differentiable function, it's quite easier to decide concavity or convexity. Why? Because you just have to look at the sign of the second derivative. You don't have to go by those definitions, those two definitions, because those two definitions, they may seem a little tricky, but still, if you go for some sort of theoretical arguments, those definitions that we have considered in this section, they are going to be very useful. And in fact, when we want to generalize to functions of several variables, those definitions will come handy. Now what we do is we take up another question. So here, let's suppose, I'll repeat that what we have taken up here is f of x is equal to mod x. This is a function which is not differentiable at x is equal to 0. Still, we have been able to prove its convexity with the help of the general definition given. In usual cases, in other cases, when we look at a twice differentiable function, it's actually easier to decide concavity or convexity because you just have to check the sign of the second derivative. You don't have to go by those two definitions given here, but theoretically speaking, those two definitions are useful. And in fact, when you want to generalize, as I said, if you want to generalize to functions of several variables, again those two definitions will prove very useful. So now let's take up another question. Suppose we have u of x, which is a concave function. So it is a concave function defined on an interval I, and g is an increasing concave function defined in an interval containing the range of u. And here we have a function f of x, so we define a function f of x equal to g of u of x. As I said, g is an increasing concave function. It is defined in an interval that contains the range of u. So the domain of g is the range of u, that is g of u of x. We have to prove that f of x is concave in I. Please keep this in mind. We don't have to go by the method, we don't have to go for the method we have used earlier, because there we talked about differentiability assumptions also. Here we don't have any of those assumptions with us. So we have to prove that f of x is concave in I. That means we have to go for the general definitions. And for that, again, we take up, let's try to solve this. Let's try to prove that f of x is concave in I. So let a and b belong to I, a less than b. Also, we have lambda belonging to this. And if I want to think of the definition of f, and let's take up f of 1 minus lambda a plus lambda b. This is in fact equal to, now f of x is equal to g of u of x. So this is equal to g of u of x. So it's exactly this. So now it is 1 minus lambda a plus lambda b. I know that I started with the fact that u of x is a concave function. So u is concave. That just means I can write u of 1 minus lambda a plus lambda b. This is greater than equal to 1 minus lambda u of a plus lambda u of b. This is because u is concave. We already know that. I know that g is increasing. This is also what I have written here. G is an increasing concave function. So g is increasing. If g is increasing, so g is increasing, and what does that mean? That just means that if you have r greater than equal to s, that implies g of r is greater than equal to g of s. Now I know that g is defined in an interval that contains the range of u. So now if I apply g to this inequality, this sign will not be reversed. So now what we do is we apply g to this, and we will have g of u of 1 minus lambda a plus lambda b greater than equal to, again, g of 1 minus lambda u of a plus lambda u of b, this. I know that g is also concave. If you can recall, I had written g is an increasing concave function. So g is increasing. For that, from that we have deduced this. We also know that g is concave. If g is concave, what does that mean? That just means that I can now write g of 1 minus lambda a okay, I can just write this, g of 1 minus lambda u of a plus lambda u of b. This should be, I know that g is concave, so this has to be greater than equal to 1 minus lambda g of u of a plus lambda g of u of b. So this expression 1 minus lambda g of u of a, and this expression and this term lambda g of u of b, this can then be written as 1 minus lambda f of a, and this can then be written as lambda f of b. And this expression is nothing but what we have started with, is that this expression is nothing but this. So I can now have f of 1 minus lambda a plus lambda b greater than equal to 1 minus lambda f of a plus lambda f of b. And that just proves, therefore, or let me write Thus, f is concave. Now, before we wind up, we just consider a very easy test for strict concavity and or strict convexity. So that's a very simple thing. It's not related to the general definition. So we are going to consider here the test for strict concavity or strict convexity. And here I can write, the first point is, if we have f double prime x less than 0 for all x belonging to this open interval, that just means f of x is strictly concave in A to B. And then I can write, if f double prime x is less than 0, if it is greater than 0, I have taken up that case. If it is greater than 0 for all x belonging to A to B, this open interval, this implies f of x is strictly convex in A to B. One very important point to note here, that you just cannot go for reverse implications here. What I'm saying here is that when we have f double prime x greater than 0 for all x belonging to A to B, for all x belonging to this open interval, that implies f of x is strictly convex in A to B. It is strictly convex in this open interval. So the fact that f double prime x is greater than 0, this is a sufficient but not a necessary condition for f to be strictly convex. We know, and we have done this earlier, that if you have a function which is f of x is equal to x raised to the power 4, we know that this function is strictly convex in this interval. This is strictly convex in this interval. But we know that f double prime x is not greater than 0 everywhere. Why do I say this? Because you have a number 0, as in we have, if I calculate f prime x, it is going to be 4x cubed. If I calculate f double prime x, it is going to be 12x squared, which is 0 at x is equal to 0, and this 0 is obviously in this interval. So f double prime 0 is equal to 0. So what does that mean? That means the fact that f double prime x is greater than 0 is a sufficient condition for f to be strictly convex. It is not a necessary condition. We have a function which is strictly convex, but f double prime 0 is equal to 0. We can't say that f double prime x is greater than 0 everywhere. This, if you just want to recall how that function looks like, it looks like this. Here we have, in this case, the function is strictly convex in the interval minus infinity to infinity, but we know that f double prime x is not greater than 0 everywhere. F double prime 0 is equal to 0 in this case. There is one more point we have to consider, that if I want to take up some of the commonly used functions that are concave in their domains, those functions would look like these. So we have concave functions, and if I have ax squared plus bx plus c, so when a is less than or equal to 0, it is a concave function. If you take up x raised to the power a, and when I talk about x raised to the power a, when a lies between 0 and 1, both inclusive, and x is greater than 0, it is a concave function. Also, if you can just recall, the natural logarithmic function is a concave function. If I want to think of some of the very commonly used, some of the most commonly used convex functions, those would be these. I can take up ax squared plus bx plus c and a greater than or equal to 0. X raised to the power a is greater than or equal to 1, x greater than 0. Then we have e raised to the power ax, wherein I obviously know that it is a convex function. Also, if I take a look at this is also a convex function. One more point, and that is the fact that if you take up a non-negative linear combination of concave functions, that's going to be concave. Or if you take up a non-negative linear combination of convex functions, that will turn out to be convex. So that's something we have to keep in mind while solving the questions, that if I have a non-negative linear combination of concave functions, that is concave. And similarly, I can write this. Non-negative linear combination of concave functions is concave. Non-negative linear combination of convex functions is convex.